Navigating unstructured outdoor environments is one of the hardest problems in robotics. And when those environments contain moving obstacles, the challenge multiplies. Most modern approaches either demand thousands of hours of robot-specific data, or they rely on reinforcement learning trained in simulation. Both paths come with massive trade-offs. Either you're bottlenecked by data collection, or you're fighting the sim-to-real gap with black box policies that behave unpredictably the moment they hit the real world. But what if you could bypass training entirely? What if you could build a robust, interpretable dynamic obstacle avoidance system using only pretrained vision models and explicit geometric reasoning? That's exactly what this paper does. The reason this gap exists comes down to two competing paradigms in modern robotics. End-to-end learned models like Robot Transformer have shown incredible generalization, but they require massive, robot-specific datasets. Training from scratch isn't scalable. On the other hand, simulation-trained reinforcement learning policies avoid data constraints, but they introduce the sim-to-real gap. Visual realism, contact dynamics, and environmental diversity never fully transfer. Worse, RL policies are opaque. You can't easily guarantee their behavior in complex, unstructured terrain. So researchers have turned to sensor alternatives, but stereo depth degrades beyond 10 meters, and LiDAR is too sparse for small or distant obstacles. Vision wins here because monocular depth models can provide dense, reliable estimates up to 30 meters, giving robots the reaction time they actually need. The author's approach leverages three key pretrained foundation models to compute time to collision, or TTC, entirely in zero-shot. The pipeline starts with UniDepth, a transformer-based monocular depth estimator. Unlike relative depth methods that require post-hoc scaling, UniDepth is trained to output geometrically consistent metric depth by conditioning directly on camera intrinsics. It takes a single RGB frame and outputs a dense depth map. From there, the system tracks 2D keypoints across consecutive frames using SuperPoint and SuperGlue. SuperPoint detects and describes features using self-supervised homographic adaptation, while SuperGlue matches them using a transformer-based graph neural network. This attention mechanism allows it to maintain correspondences even in low-texture or ambiguous regions, which is critical when tracking obstacles like tree branches or uneven terrain. Once you have 2D tracks, you need to lift them into 3D. The system uses the standard pinhole camera model, combining the 2D pixel coordinates with UniDepth's predicted metric depth, and the camera's intrinsic matrix to backproject each keypoint into camera frame 3D coordinates. Specifically, x is calculated as u minus cx times z divided by fx, and y follows the same pattern for the vertical axis. But raw backprojection is noisy, so the pipeline runs a 5-frame sliding window through the XM solver, which handles scaled bundle adjustment. The XM solver is particularly interesting because it reformulates the bundle adjustment problem as a semi-definite program relaxation. Instead of relying on local gradient descent, which easily gets trapped in suboptimal minima, it uses a low-rank Riemannian optimization framework based on Bura-Montero factorization, paired with a custom CUDA-accelerated trust region method. This guarantees a mathematically certifiable global optimum. Now here's the crucial caveat: the solver is strictly geometric. It will find the optimal solution relative to its inputs, which means any systematic scale bias or depth discontinuity from UniDepth will propagate directly into the final trajectory. To mitigate this, the system filters out keypoints that move more than 2 meters between frames, discards points beyond 20 meters, and reinitializes any trajectory that shows a sudden displacement jump. With optimized 3D trajectories in hand, the system computes velocity via linear regression. For each keypoint, it calculates the closest point of approach relative to the camera and discards anything beyond 3 meters. Then comes the TTC calculation. The formula is straightforward but physically grounded. TTC equals the keypoint's metric depth divided by its radial velocity toward the camera. This only yields a finite value for points actually approaching the robot. Stationary or receding points are ignored. The system then identifies the keypoint with the minimum TTC, computes its closest point of approach in 3D space, and generates a two-dimensional motion primitive on the ground plane that pushes the robot away from that threat vector. The pipeline was evaluated on the M3ED dataset, which features a Boston Dynamics spot quadruped navigating forests and urban environments. The authors set a TTC threshold of 1 second, which aligns with the robot's nominal speed of 1 meter per second, leaving roughly a 1-meter buffer for evasive action. In terms of frame-level classification, the system achieved a precision of 0.49 and a recall of 0.38 for detecting frames below that 1-second threshold. On paper, that recall looks low, but it tells a different story in practice. Across all sequences, the pipeline successfully flagged at least one threatening frame for 20 out of 22 unique physical obstacles. In a real deployment, once the first danger is detected, the evasive maneuver is already initiated, making subsequent missed detections irrelevant. When a threat was correctly identified, the system generated the correct evasive direction 84% of the time. So why isn't the recall higher? The authors identify two main failure modes. First, many missed detections weren't caused by bad TTC estimates, but by a complete lack of tracking. SuperPoint and SuperGlue sometimes fail to maintain correspondences across long sequences, especially in low-texture areas. If a keypoint isn't tracked for the required 5 frames, it's excluded from bundle adjustment and TTC computation entirely. Second, even when tracking succeeds, monocular depth inaccuracies can create discontinuities in the 3D trajectory. The system detects these jumps and reinitializes the track, which temporarily removes the point from the TTC window. Because the XM solver is purely geometric, it optimizes around these flawed constraints, sometimes producing distorted trajectories that trigger false positives or mask real threats. To push this further, the authors suggest replacing SuperPoint and SuperGlue with more robust long-term trackers, like DroidSlam features or a Kalman filter-augmented correspondence pipeline, to maintain tracks through motion blur and textureless regions. Full end-to-end deployment on the Spot robot, measuring real-time latency and integrating with the locomotion controller, is the next critical step. But the core achievement here is profound. By leaning on pretrained vision foundation models and explicit geometric reasoning, this approach completely eliminates the need for robot-specific training. The entire system required just 74 seconds of data, solely for hyperparameter tuning. It's a compelling proof that we don't always need to train massive models from scratch or rely on simulators. Sometimes, the right combination of pretrained perception, geometric optimization, and interpretable motion planning is enough to build robust, generalizable robotic control. If you're interested in the math, the dataset, and the full architecture, I'll leave a link to the paper in the description. Thanks for watching, and I'll see you in the next one.